Let's talk about the idea of a monotonic sequence. Now, sequence AN is said to be monotonic if its terms are either non-decreasing or if the terms are non-increasing. So, something that was non-decreasing may look something like this, where I have 1, 2, 3, and so forth. If I have a sequence that looks like this, it may level off, but then pick up again. The point here, if I look at each successive term, it's either greater than or equal to the previous term. So there's nowhere in here, you can't find a stretch of terms that the values are actually decreasing. Okay, so this is non-decreasing. If it's non-increasing, then it's a similar idea, where perhaps we have terms doing this. Again, each term is smaller than the previous. So nowhere in there am I actually increasing. It's possible that I could have a couple terms that are equal to each other, and then drop off, equal, drop off, that sort of a thing. But the point is, it's never, ever is it increasing. Something like this one, we would tend to think of as being specifically monotonic increasing. And this I would think of as being monotonic decreasing. So take a look at an example. If I have a series that simply consists of 5 plus -1 to the n, then the values will be, for n equals 1, it'll be 4. For n equals 2, it'll be 6. For n equals 3, it'll be 4. N equals 4, it'll be 6. So it's going bouncing back and forth, 4, 6, 4, 6, 4, 6. So if I were to graph this, 1, 2, 3, 4, 5, and let's say here's a line y equals 5, and down here I have 4 and 6. At 1, I'm at 4. At 2, I'm at 6. At 3, I'm at 4. At 4, I'm at 6. At 5, I'm at 4. So I'm going to be increasing, then decreasing, then increasing, then decreasing, and so forth. This is not monotonic. This is definitely not monotonic, because I have a combination of increases and decreases. Something like an equals 4n over n plus 1. Well, with this, I'm going to equate this or think of this as f of x equals 4x over x plus 1. Now, it's true for every n, because remember the domain of n is 1, 2, 3, 4, all to infinity. For every n, an equals f of n. So they're equal everywhere. So now that I'm thinking about it in terms of this continuous function, I'm going to take a derivative. Let's take a look at f prime of x. F prime of x equals 4 times x plus 1 minus 4x times 1 divided by x plus 1 squared. Well, that's going to be 4x plus 4 minus 4x over x plus 1 squared, which obviously the 4x is a cancel, which is 4 divided by x plus 1 squared. Now, if we look at this, this is positive everywhere. This is greater than 0 for all x, and I'm really only interested in our domain. And it's true that this is positive for all x that it's defined for. The only value where it's undefined is x equals -1, but that's outside of our domain, so we're not even interested there. So if the first derivative is positive, that means that if I'm positive everywhere in the domain that we're interested in, that means that the function is increasing everywhere. Therefore, an is monotonic increasing. Taking a derivative of the original function, thinking about it in terms of equating it to a continuous function, then taking the derivative, that's a quick way to figure out whether I have monotonicity or not. If this function were to change, it's positive at one area and a negative in another area, looking for critical values just like we normally do back in Calc 1, then it's telling me that this is not monotonic. I can maybe find certain areas of the domain where I have monotonicity over that limited area of the domain, but in general, this may or may not be monotonic. But I can tell specifically by the first derivative. If the first derivative is negative, it's monotonic decreasing. If the first derivative is positive, it's monotonic increasing.